Go back to the moment Zero Trust was supposed to fix 6 episodes ago. Kestrel's attacker didn't break anything to get from the scheduling service to the billing service. They used a contractor's credential, the same credential that account had used 100 times before, over the same VPN, during the same business hours, and the billing service let it through because it arrived from an address inside the right subnet. Zero Trust said the fix was to verify every request against an identity, at every hop, no exceptions. That's the right answer, and we spent an entire episode on it. But it leaves a question dangling that we never actually answered. Verify against an identity how, exactly? A subnet isn't an identity. A static credential sitting unrotated for weeks isn't an identity either. Not in any sense a security architect should accept. This episode, and the arc it opens, is about the actual mechanism enterprises use to answer that question for real people and real services requesting real things. OAuth 2.0 and the identity layer built on top of it. OpenID Connect. Get comfortable, because this is the part of Zero Trust that most architects think they already understand, and mostly don't. Here's the confusion that causes more real security incidents than almost any other single misunderstanding in this space. OAuth 2.0 is an authorization framework, not an authentication protocol. And treating it as one isn't a pedantic distinction. It's the design mistake that creates real vulnerabilities. Authentication answers one question: who is this? Authorization answers a completely different question: what is this party allowed to do? OAuth was built from its first draft to answer only the second question. It exists to let one application obtain limited access to a resource on another application, on a user's behalf, without ever handing over that user's password. A photo printing service that needs read access to your photos stored somewhere else. That's the problem OAuth was designed to solve, and it solves it well. The trouble starts when an architect looks at an OAuth access token arriving at an API and treats its mere presence as proof of who the caller is. An access token proves that some client was granted some scope of access by some authorization server. At some point before it expires, it says nothing reliable about the identity of the underlying user, because access tokens weren't designed to carry that information in a standard, verifiable way, and plenty of valid access tokens get issued for machine-to-machine flows where there's no human user behind them at all. Build an authentication decision, a login, a session, this is definitely the account holder assertion, on top of a bare access token, and you've built exactly the kind of implicit trust gap that let Kestrel's attacker move from scheduling to billing. Something that looks like verification that isn't actually verifying identity at all. This is precisely the gap OpenID Connect exists to close, and we'll get to how in a few minutes. But the underlying discipline matters more than any one spec. Know which question you're actually asking before you pick the tool that answers it. OAuth 2.0 is defined in RFC 6749, published by the IETF, and it's worth reading in the original at least once if you design systems that touch it, because most of what teams get wrong traces back to skipping the spec and working from someone's blog post instead. The framework defines 4 roles that show up in every flow. However, the flow itself varies. The resource owner is the user, or occasionally another system that owns the data being accessed. The client is the application requesting access, the photo printer, the mobile app, the internal service. The authorization server is what actually authenticates the resource owner and issues tokens once they approve the request. And the resource server is where the protected data actually lives, the API that has to decide on every call whether the token presented to it is good enough to grant access. RFC 67499 defines several ways a client can obtain a token, called grant types, and this is where a lot of legacy guidance has aged badly. The authorization code grant, where the client gets a short-lived code and exchanges it server-side for a token, is built for exactly this: an application acting on behalf of a human user who's present to approve the request. Client credentials grant exists for pure machine-to-machine access, no human involved at all. There's also device code flow for input-constrained hardware, like a smart TV. What matters architecturally is narrower than the full list. For anything user-facing, there is essentially one grant type you should be reaching for today, and we're about to walk through exactly why. Walk the flow the way it actually happens on the wire, because the sequence itself is the security model. The user clicks log in inside the client application. The client redirects the user's browser to the authorization server, along with a code challenge, a value derived from a secret the client generated just for this request and never sends anywhere in the clear. The user authenticates directly with the authorization server, not with the client, which matters because it means the client application never sees the user's actual password. The user approves the requested access. The authorization server redirects back to the client with a short-lived authorization code, typically valid for under a minute. And here's the step that used to be missing, and where the vulnerability lived. The client exchanges that code for an access token by calling the authorization server directly, presenting the original secret alongside the code so the server can verify that whoever's redeeming this code is the same party that started the request. That verification step is PKCE, proof key for code exchange, defined in RFC 7636, and it exists to close a specific, real interception risk. On a mobile device or in a single-page application, there's no reliable way to keep a traditional client secret confidential, because the client application itself ships to the user's device, where anything embedded in it can eventually be extracted. Without PKCE, a malicious app on the same device that intercepts the redirect containing the authorization code could redeem that code itself before the legitimate app gets to it, and walk away with a valid access token for someone else's session. With PKCE, that intercepted code is worthless on its own because redeeming it requires the original secret, the code verifier, that only the legitimate client ever generated, and that secret never once crossed the network in a form an interceptor could reuse. This is why current ITF guidance on OAuth security best practices treats authorization code flow with PKCE as the default for every client type, not a special case reserved for mobile apps. There's no longer a good reason to run it without PKCE, even for a traditional confidential server-side client. So treat this as the baseline, not an exception. Two other grant types from the original RFC 6749 show up constantly in older code bases and in outdated tutorials still ranking on search engines, and both deserve active removal wherever you find them. The implicit grant was designed for browser-based applications that, at the time RFC 6749 was written, had no reliable way to make a server-side token exchange call. Instead of a code, the authorization server handed the access token straight back in the URL fragment after redirect. That token now lives somewhere browsers were never built to protect carefully. Browser history, server access logs, if any proxy along the way, logs full URLs, and the referrer header of any subsequent request the page happens to make. There's no exchange step to verify who's redeeming anything because there's nothing left to redeem. The token's already out in the open. The OAuth working group formally recommends against implicit grant now, precisely because authorization code flow with PKCE solves the same original problem. A public client with no confidential secret. Without ever putting a live token somewhere a browser has to keep safe by accident. Resource owner password credentials grant is the more dangerous of the two because it looks harmless. The client just collects the user's username and password directly and trades them for a token. That defeats the entire point of OAuth. The reason this framework exists at all is so a client never has to see, store, or transmit a user's actual credentials, and ROPC hands those credentials straight to the client anyway, which means you're now trusting every client application with the one secret OAuth was built to protect. It also can't accommodate multi-factor authentication cleanly, since there's no interactive step where the authorization server can prompt for a second factor, just a single request carrying a username and a password. If you find ROPC in a design today, the honest read is almost always that it's a shortcut taken because implementing a real redirect-based flow felt like more work, and it deserves treating as a finding, not a preference, the same way an undocumented trust relationship between two internal services was a finding at Kestrel. OpenID Connect is where the authentication gap actually gets closed, and it's worth being precise about what it is. OIDC is a thin, standardized identity layer built directly on top of OAuth 2.0, defined in OpenID Connect Core 1.0 by the OpenID Foundation, not a competing framework and not a replacement. It reuses the exact same authorization code flow we just walked through, with the same redirect, the same code exchange, the same PKCE protection. What it adds is one new artifact and two new endpoints, and each one earns its place. The new artifact is the ID token, a JSON web token, a signed, structured piece of data the authorization server issues alongside the access token in the exact same response. Unlike an access token, the ID token has a standardized shape. It carries claims: who the subject is, which authorization server issued it, which client it was issued for, when it was issued, and when it expires, all cryptographically signed, so the client can verify the token actually came from the authorization server it expected and wasn't tampered with in transit. This is the piece that was structurally missing from plain OAuth, a verifiable, standardized statement of identity, rather than an access token whose contents and format an architect had to guess at or invent locally. The two new endpoints round it out. The userinfo endpoint lets a client, holding a valid access token, ask the authorization server directly for additional profile details about the authenticated user, name, email, whatever the granted scope allows, without that information having to be crammed into the token itself. And discovery, published at a standardized path /.wellknown/OpenID configuration, lets a client fetch a single JSON document describing every endpoint, every supported signing algorithm, and every capability of a given identity provider automatically, instead of an architect hand-configuring URLs that quietly drift out of date. Put together, ID token, user info, and discovery are the entire delta between OAuth and OIDC. Everything else is the OAuth framework we already covered, doing exactly what it always did. 3 token types show up across this whole system, and conflating them is where a lot of production incidents start. The access token is what the client presents to a resource server on every API call, and its only job is authorization, proving to that specific API that this client was granted this specific scope of access for a limited window of time. It's opaque as far as the spec is concerned. Some authorization servers issue it as a JWT and some don't, and a well-built client shouldn't assume it can read the access token's contents at all, only that it can hand the token to the resource server it was issued for. The refresh token is different in both purpose and handling. It's a long-lived credential, issued alongside the access token, whose only job is getting a new access token once the current one expires, without forcing the user to log in again. Because it's long-lived and powerful, anyone holding a valid refresh token can mint fresh access tokens indefinitely. It needs to be stored somewhere considerably more protected than an access token, and it should never be sent to a resource server or exposed to anything running in a browser tab if it can be avoided. The ID token is the OIDC addition, and its job is authentication, full stop. It's meant to be validated once, at the moment the client receives it, to establish who logged in, and then set aside. It is not meant to be attached to ongoing API calls the way an access token is. That's a genuinely common architectural mistake, sending the ID token to a resource server as if it were an access token, when the resource server was never one of its intended recipients and has no reliable way to know what to do with it. 3 tokens, 3 separate jobs: access token for authorization on each call, refresh token for staying logged in without reprompting, ID token for establishing identity once at the start. 2 more terms get used almost interchangeably in casual conversation and shouldn't be, because they answer different questions at different points in the flow. A scope is requested up front before any token exists, and it describes what access the client is asking for. Read access to a calendar, write access to a billing record, profile information at all. Scopes are what the user actually approves on the consent screen, and what the authorization server checks against before it issues anything. They shape the token. They answer the question, what is this client allowed to do? A claim is a piece of information that ends up inside a token, typically the ID token, once it's issued. A statement about the subject, like their email address, their name, or the time they authenticated. Claims answer a different question. What do we now know about this identity? The relationship between the two is that requesting certain scopes is usually what unlocks certain claims. Request the profile scope, and you're telling the authorization server you'd like the claims that scope maps to included in the resulting ID token. Get this distinction backward, and you end up either requesting far more access than an integration needs because you conflated a scope with a claim you actually wanted, or building an authorization check against claims that were never guaranteed to be present, because the scope that would have populated them was never requested in the first place. Here's where this connects directly back to what actually happened at Kestrel, because the contractor credential that got phished wasn't just weakly verified, it was long-lived. It worked for weeks after being harvested, because nothing about it expired on any schedule short enough to matter. The equivalent failure in an OAuth deployment is an access token issued with a lifetime measured in days, or worse, one that never expires at all, because a team decided constant re-authentication was too much friction for users, or for internal services calling each other. The actual defense architects should be designing for is short-lived access tokens paired with refresh token rotation. Access tokens should live for minutes, not days. The shorter the window, the smaller the damage if one is ever intercepted, because it's simply not valid for long enough to matter to whoever stole it. The refresh token is what makes that short lifetime tolerable for the user, silently getting a new access token behind the scenes without forcing a fresh login every few minutes. Rotation is the piece that closes the remaining gap. Every time a refresh token is used, the authorization server issues a brand new refresh token and invalidates the old one. If a stolen refresh token ever gets used by an attacker, and the legitimate client tries to use its now invalidated copy afterward, that reuse is itself a detectable signal, a strong sign the token was compromised, at which point a well-built authorization server can revoke the entire token family immediately, cutting off both the attacker and forcing the legitimate user to simply log in again. Picture this applied at Kestrel's actual boundary. If the scheduling service had called the billing service using a short-lived service-level access token instead of a static, long-lived credential, that phished credential's value collapses from 6 weeks of usable access down to whatever the token's lifetime happened to be. Plausibly, minutes. The attacker still would have had a foothold. They would not have had 6 weeks of quiet lateral movement to build on top of it. That gap, long-lived static credential versus short-lived rotated token, is a large share of the actual architectural distance between what Kestrel had and what a modern identity-aware boundary looks like. 3 mistakes recur constantly in how enterprises actually implement this. The first is exactly where we started, treating a bare access token as proof of identity, building login decisions or authorization logic on top of it without ever validating an ID token or confirming the token was even issued through a flow that authenticated a real user. The second is defaulting to whatever grant type a tutorial or an old internal wiki page happened to demonstrate, rather than deliberately choosing authorization code with PKCE for anything user-facing, which is how implicit grant and resource owner password credentials keep showing up in production systems years after the specs themselves moved on. The third is configuring token lifetimes for convenience rather than for risk. Long-lived access tokens because refreshing them felt like unnecessary engineering work. Static service credentials between internal systems because rotating them seemed like a problem for later. That third mistake is precisely the one sitting underneath Kestrel's billing and scheduling gap, just wearing a different name depending on which system you're looking at. Underneath all three is the same root pattern this season keeps surfacing. Architecture that looks correct on a slide, using all the right vocabulary, without anyone having actually verified what the tokens do, how long they live, and what happens the moment one gets stolen. OAuth and OIDC answer how a single application verifies who's calling and what they're allowed to do. They don't answer a related question that gets harder the moment an enterprise has more than one identity provider, a legacy system still running an older federation standard, and a partner organization that needs access to some of it. How do you carry identity across boundaries between separate organizations and separate trust domains? Not just between a client and one authorization server. That's SAML's original problem, and it's still very much alive in real enterprise estates, often running right alongside OIDC rather than being cleanly replaced by it. Next episode, we put SAML and OIDC side by side in SAML versus OIDC, federation patterns in enterprise estates, and work out where each one actually belongs. If you're building systems that need real, verifiable identity at every hop, not just the appearance of it, subscribe, and I'll see you in the next one.